need to be on your best behavior.
That's not true. Low bar.
Yeah, I'm recording it.
Stop talking.
So,
No looking at the bird.
so front row, behave. Okay, so I was getting my girlfriend a cup of coffee this morning at the coffee shop next door, and I got her a mocha, and I was carrying it in this tiny little paper cup. I was walking back to my place, and and every step that I took, this mocha, the bottom of the cup, the little paper cup, it would click. It would do this, like, it would go from being like diaphragm up to diaphragm down, diaphragm up to diaphragm down, every step that I took. And it was really fun. And so I was enjoying this as I was walking. And then I thought maybe I would do an example in class today of a model of this. Okay? So let's lumped parameter model this thing. So we have a cup of coffee. So, I'm not the best artist professor. I know this about me. And, it's got liquid in it. And I'm walking with it, it's moving up and down, right? It's moving up and down. And the bottom of this thing goes from like down to up, back and forth. Now, we can probably model this fluid as being a lumped mass. Okay, it's some mass that's actuating the bottom of this cup. I wish I would have brought the cup and I could have like blown. It would have been like. Would have been cool, but anyways, so this is the, so let's lump parameter model it as being a mass, a lumped mass, and we could find what that mass is by finding what the volume of the liquid is plus the volume of the liquid times the density of the liquid, the whipped cream, the sprinkles. We could add that on. As well, and that's the mass that's actuating this thing at the bottom. And I know that the bottom of this thing has some sort of spring-like action because it takes some force to displace it, right? It takes some force to displace it, and it wants to pop up. So if I don't step hard, it doesn't completely pop down and pop back up. So it has this sort of springiness to it. And it's probably very nonlinear, if we're honest about the situation. It's probably pretty nonlinear, but let's hope, the first time through we can get away with a linear spring model for that action. So we've got a spring, and that spring is connected to something, and it's something that is actuating the system. So it's connected to this cup. And the cup, I'm moving it, right? As I walk, I'm moving it up and down, essentially. I'm walking forward, but at a constant velocity. Mostly what it's experiencing is the up and down motion. Okay, so probably we could model that as being a force, but a better model would probably be a velocity model, a motion model, right? I'm moving it, and it's responding accordingly. So we could think of there being a velocity source here coming in. And it looks like, something like this, right? Like it's going, I'm moving it up, and I'm moving it down, I'm moving it up, and moving it down. And something that I also observed was that if I stopped, it did not continue to move up and down. It did not continue to, like the fluid did not continue to go up and down and go. That would have been cool, but it did not happen. And so therefore, energy must be leaving the system, right? So we got to have a damper in there. And the energy is leaving the system because there's a fluid in there moving around, sloshing around, and heating up some very small amount, right? So that fluid is damping out this motion. So let's also connect a damper up here. And it's mostly damping based on the relative motion of the cup and the liquid, right? It's moving around. I'm moving it up and down. So there's, I mean, it's very complicated, right? The fluid's moving, swirling and twirling and all kinds of stuff. And there are bubbles in it. Stuff's happening in there. But we know the energy is leaving it somehow. The spring constant, K, we probably could measure. I mean, like I said, it's probably nonlinear, but if we took it to be semi-linear, or if we just decided to take the measurements and see what it was, we could put some known force in, and we could measure what the displacement was, and maybe it's actually linear. Who knows? But it's probably more like some weird thing, right? Or this. But let's say it's linear, and that there's some spring constant K that we could use to describe that spring. Okay. And B is always hard. Coming up with a value of B for this problem, I don't like our chances, frankly. But I think that what we could do is we could take some measurements of it, and we could back out what B is. And you guys will do some in the lab where you guys will be measuring some parameters in your model through experiment. Okay, so here's a reasonable lumped parameter model in terms of a schematic, right? Now, our next step is to draw a linear graph for it. Okay, we want to draw a linear graph for it. So we've got the physical sketch, we've got a lumped parameter model schematic here. And now let's draw a linear graph. Now, it's a mechanical translational linear graph. We're going to always have a reference here, right? So we have a reference node. Let's take that reference node to just be 0 velocity. And we've got, whenever there's a mass in our system, we have a mass node, right? So there's going to be a mass node. The mass node always connects to ground because the elemental equation for the mass node is F equals ma, Newton's second law. So we've got to have that inertial reference frame. Okay. And we also have the cup motion, right? So we've got the cup velocity source coming in here, right? That's what's causing the motion to happen. And so we've got our velocity source. Now, what do we need to do before we draw an arrow on this? We need a coordinate arrow, right? Coordinate arrow. I drew it in the same direction as the source because stable genius up here. Yeah? Because we want to be able to use the nice memory that we have of, if they're drawn in the same direction, then we draw the across variable source arrow direction away from the node of application, right? Okay. So that was in our sign convention lecture, where we said that whenever we have an across variable source, if the coordinate arrow is in the direction of the across variable, so if we draw them in the same direction, then the arrow on the linear graph goes in the opposite direction of the node of application, away from the node of application. The node of application here is our cup velocity, you could say. Okay? We can think about the mass here of this volume of this liquid as moving. When the bottom of it dips down, we think of that whole volume of fluid dropping down, right, relative to the cup. So the cup is here. The volume just goes in the cup. So the cup velocity is the node of application, and then it connects to the mass of the fluid through two elements, the spring and the damper, right? K and B. And in our sign convention, we said to draw these in the direction of the coordinate arrow, which in the coordinate arrow in our system is from the cup node to the mass node. So we draw them from the cup node to the mass node. And also remember, if we got those arrows wrong, NBD, right? We just have to interpret the end. At the end, it has to be interpreted differently. But yeah. So we've got our linear graph model, and I feel pretty good about it. I feel like this is a good model. I mean, for a back of the envelope kind of thing. We're sitting down at coffee and we just want to work it out. So we've got this, and we want the first step we need to do for going from a linear graph model to a state space model, which is what we would like to have. And that state space model is the best type of model you can have for a dynamic system, because you can do all kinds of stuff with it. You can throw it into MATLAB easily, do some simulation with it. You can solve it analytically, which I'll teach you guys how to do next semester. But you don't have to combine all your equations into one differential equation and find the homogeneous solution and blah, 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 blah. You don't have to do that. There's one solution technique that I'll teach you guys how to do. So we want that state space model. From there, we'll learn how to solve all of the state space problems in one swoop. Okay? So we want that state space model. Our first step is to draw a normal tree. So I think in the algorithm you guys have, what's that lecture number? 3.1, 3.2, 3.3, I don't even remember. Something. The algorithm, first step is to draw the normal tree, or the linear graph or something, wherever we are in the steps. So let's get a color you guys can see. Can you guys see the green okay? Yeah? Okay. And let's draw our normal tree on top of the linear graph. So the two rules are, we got to have all nodes, so you can always start off with all the nodes. And we also have to make sure that we don't create any loops in our normal tree, right? So we select elements in descending order of priority, starting with across variable sources. So there's our across variable source. And then we've got the next thing down the list is A-type energy storage elements. We've got one here, the mass. If we add K or B in, we will create a loop, right? So we can't do it. Can't do it. Can't put K in, or can't put K in, can't put B in, or we'll create a loop. It wouldn't be a normal tree if there was a loop. Therefore, we're done. Okay. Great. So then we've got, does anybody have the algorithm pulled up? So I don't remember the numbers. I'm not going to number them because I can't remember the numbers off the top of my head. But the next step, I know, is to find the variables. Okay, the variables are, oh no, you can just read them out to me. What is 1A?
That's the continuity, so the fs minus f, well, let's see.
In the algorithm, part 2. That was today's lecture.
Draw a normal tree. Identify primary and secondary variables.
Yeah, so draw a normal tree. Bam, that was 1A.
Yep.
1B?
Identify primary and secondary variables.
All right, so this was 1A. 1B. So variables, we have primary variables. which are across variables on branches, branches being elements in the normal tree, and through variables on links, links being elements not in the normal tree. So we have across variables on branches, so VS, VM, FK, FB, through variables on links, FK, FB, force through the spring, force through the damper. The secondary variables are those that are the opposites of these. So the force from the velocity source, the force on the mass, the velocity across the spring, and the velocity across the damper. Those are secondary variables. Okay, great. 1C, state variables, right?
Okay. Cross variables on A-type branches through variables.
Yeah, so across variables on A-type branches. So we have an A-type branch right here. M is an A-type energy storage element. It is a branch in the normal tree, and therefore its across variable is a state variable. So VM. And also we need to look for links that are T-type energy storage elements. Our K here is a link, so it is a T-type link, and its through variable is our state variable there. That's all we've got of either of those types. So we've got 2 state variables. So what is the order of the system? It's equal to the number of state variables. N equals 2. 1 and 2 state variables. D. We need to put them in standard form. So the vectors, the vector value functions really, but the vectors. So we've got our state vector, which we can say is VM FK. Could I have chosen FKVM?
Yes?
Yes. It's
Yeah.
arbitrary. However, once you choose it, you got to stick with it. Okay?
Yes.
All right. There are some bad jokes that just flew into my head right then. Okay. Now we've got the input, which we've only got one source in here, right? So our input is just a 1 vector VS. And our output we haven't yet identified. So we haven't decided what we want to see come out of this thing. One thing that might be interesting for us, though, is to find the force that the source is having to apply to make that velocity happen. Okay, so what is the force that my hand has to apply to the cup? That might be interesting to know. So let's say that Fs is an output. And let's also throw in another one for fun, Vm, the velocity of the mass. See what's happening with that sloshy mocha. So those are our outputs. Okay. E comes after D. And that one states what?
Right, an elemental equation for each passive element.
Elemental equations for each passive element. So elemental. And I have 1E for elemental equations. Thank you very much.
What do you think you are, Elvis?
Ah, I wish. Nah, he's dead.
Halloween's coming up.
Okay, so M, K, and B. We can use dots because we don't have any circuits in this problem, right? Dots for derivatives? Yeah, let's do it. It's a party. Okay, so the elemental equation for a mass is just the Newton's second law, right? Vm dot equals 1 over m Fm. The elemental equation for a spring is Fk dot equals k Vk. Now, I always remember that because Hooke's law says f equals kx. Take the time derivative of f equals k times the time derivative of x, which is v. That's how I remember it. 5 people on the second midterm will write 1 over k. Do not do it. Okay. You too could be a stable genius. Okay. FB equals BVB. That's the damper elemental equation. Always the same elemental equations for masses, springs, dampers, right? They're always the same.
Okay, so but it's not dot FB, it's just FB, right?
Correct. The damper does not have derivatives, and the damper equation does not have derivatives in the power flow variables. Okay. F. Continuity equations. It's continuity. I was trying to be cute. Okay. Thank you. Okay, continuity equations. We need to draw our contours, right? Contours on our linear graph. We need to draw one contour for each element, so each passive branch. Okay, I only see one passive branch. This is an active branch because it is a source, right? So one branch is passive, which is the mass. So you need to draw a contour that cuts through just one branch element. Okay, and what's nice is that this contour that cuts through just that mass element is just the node equation, or just the node, right? And we want to write the continuity equation that corresponds to this contour. And we also want to solve that for Fm, the through variable associated with the branch that we're cutting. Okay? So what we want to write is Fm equals something. So Fm's leaving this contour, so Fm is going to equal all the force coming into it, so Fm equals Fk plus Fb. So we've got Fm equals Fk plus Fb. That's the only branch that's passive, so that's the only continuity equation we need. G, 1G, compatibility equations. Okay, so we need one for each passive link. And the links that we've got here are K and B. So the spring and the damper. So we'll write one for K. So we also want to write it in terms of the across variable associated with the link. So Vk equals, thinking of this as a vector, like vector addition, so Vk equals Vs minus Vm. Okay. We can do it again for B. Vb equals, once again, Vs minus Vm. Okay, so we've got our 3 equations of continuity and compatibility. And the next step is 2a, which is to eliminate all the secondary variables by substituting a continuity or compatibility equation into an elemental equation. So what we do is we just rewrite our M, K, and B elemental equations, but we do a substitution in each of them. So we're going to take Fm from this continuity equation. We're going to take Vk from this this compatibility equation, and Vb from this compatibility equation. So we'll get Vm dot equals 1 over m. Instead of Fm, we'll plug in Fk plus FB. Next one, we've got FK dot equals K. Instead of VK, we'll plug in VS minus VM. And finally, FB equals, I need to go get my charger. B was VB, but now it's VS minus VM. Okay. Now, the next step in this process is to take these equations and reduce it down to 2, the order of the system, to n. Order of the system, 2 in this case. 2 differential equations in only state variables and inputs. I'll give you guys a minute to think about that while I grab my laptop chair. Don't say anything obscene into the microphone.
Should we scoot the camera so that it looks like a picture?
Flash.
No, please don't.
James, do.
So he reuses the Slack anyway, so the new students will find the picture.
That's
when
the
it
point.
I just want you guys to know you're all horrible students. 100%.
Speaking of something not
Especially
entirely
you with the
related
suggestion
to
that
us.
someone turn some stuff in. You can't suggest anything to this kid. He's going to do it. There's no matter.
That's like half the point. You gotta
goes.
find the friendly, extremely suggestible person, and then you get them to do all the terrible things.
That's like taking answers to the special needs classroom and telling everyone you brought Kool-Aid. Right.
Don't say anything obscene into the microphone, kids.
You can always just cut it out.
I hope he goes through this before he goes.
What's that mean?
I'm kind of wondering if he can even hear, because half the time if he watches videos, you can't hear anything.
Yeah.
Like, you can't hear anything besides him, so you okay.
James said some very obscene stuff. You
I
need to check
did
it before you
not.
do it.
I suggest plug B into M and then call it a day.
Yeah, that's a very good suggestion. So let's do that. So we've got FB being the final remaining variable that's not a state variable or an input. Those stairs, you know, all right? Definitely not out of shape or anything. So we need to plug that equation into there. So 2b is to just rewrite these as, so Vm dot equals 1 over m Fk plus b Vs minus Vm. Great. And then the Fk dot equation is the same, right? K Vs minus Vm. We don't have to do anything to this because Vs is an input, Vm is a state variable. So we're good. You got it. 2c is to write these state equations into a single vector state equation, the standard form. And that standard form is always x dot equals ax plus the A matrix plus the B matrix U. Now we've got B for damping, we've got B for the B matrix. Not ideal in the same problem, but they are always the A, B, C, D matrices. We could have used C for the damping. That would have been a little bit better. But C is also so the two variables that are often used for damping are B and C. C is also one of our matrices. So you just, I don't know. I should do like B under bars or something, which means the matrix. Have you guys seen that notation?
Have now.
Have now, all right. So these are the matrices. So we need to do x dot, which is Vm dot Fk dot. Okay, so that's the state vector in the order we chose it to be, right? Vm Fk, and then the time derivative of it. It's equal to the A matrix, which has got to be, it's got to end up being dimension 2 after we multiply x. It has to end up being 2 on this side because it has to match up with this vector on the left-hand side. So if it has to be a 2 by, this dimension has to be 2. The other dimension has to be 2 because it has to multiply x, which is a 2 vector. So it's to be a 2 by 2. It's always an n by n. So the 2 by 2 multiplying the x vector, which we'll write out, Vm Fk, plus the B matrix, which has to be a 2 by something because it has to add to the 2 by 1 vector. So 2 by something multiplying U, which is a 1 by 1 vector. So a 1 vector. So it has to be a 2 by 1 matrix. And our input U is just Vs. So this is going to be our A matrix. And this is going to be our B matrix. Okay. So Vm, that equation is going to come from here, right? So we need to rewrite that first row is going to be rewriting this equation. Anybody mind shedding that? Thank you. How dare they maintain these grounds during class? Unbelievable. Okay, so let's rewrite this. Let's rewrite this into the first row. So we're looking for so this term is going to multiply Vm, so we need to be looking for the Vm coefficient first. Looks like we have a negative b, and then we have an over m. So negative b over m, Vm, plus, we got to do the Fk term now. So what's the Fk coefficient? 1 over m. Very good. And then we've got the Vs coefficient. We've got Vm coefficient is, sorry, the Vs coefficient is b over m. Very good. The next equation is the Fk equation. So Fk dot equals something times m. Is it k or negative k? Yeah, negative k. And then how many Fk's are there? 0 Fk. And then we have Vs, which is what is the coefficient of Vs? Okay. Boom! State equation. Done. Standard form. Done. Okay. 2D. I put the dots there, so I'm going to stick with it. I need to write the outputs in state variables and inputs. So before I can put them in standard form in the next step. So our outputs, we chose them to be Fs and Vm. So if I chose them to be Fs and Vm, I need to rewrite these in state variables and inputs. So Fs, we haven't used Fs at all, right? Fs is something that we are able to avoid completely unless we happen to ask for an output that is in terms of Fs. So Fs is coming in for the first time. So we don't have an equation for it yet because we haven't even bothered to write it down. But one weird thing on sources to remember is that the through variable on an across variable source actually goes the opposite direction of the arrow. And I know that's weird, but it is the case. So our Fs is going that way. Okay? So if we were to look at a contour here, we would see that Fs goes into this contour or node, and Fk and Fb go out. So fs has to equal the sum of those two, right? Fs has to equal fk plus fb. Which makes sense, right? It's the sum of the spring force and the damping force that are connecting that mass to the cup, and that's the force that the cup is going to have to be forced at in order to make the motion that's happening. So Fk plus Fb. Fk is a state variable, but Fb is not, right? So we're going to have Fk again, plus we got to come up with an expression for Fb in terms of state variables and inputs. Oftentimes during this process, you can find an equation, an intermediate equation in the solution that you've come up with so far to find the state equation for the output variable or part of the output. So Fb equals B Vs minus Vm, and that's an input and a state variable, so we're good to go here. B Vs minus Vm. And we have state variable, input, state variable, so we're good. How do we write Vm as a state variable or an input? It is a state variable.
Yeah.
Yeah. That one was easy.
Yeah.
Okay. So now we've got the last step, 2e. We need to write the output in standard form, which is always y equals the C matrix x plus the D matrix u. Okay, so our output here we could write as Fs Vm equals, the C matrix has got to be 2 by because it's come out with a 2 vector, so a 2 by, and then x is 2, so it happens to be a 2 by 2. It doesn't always come out to be the same, we don't always have the same number of outputs as state variables. That was just an accident, okay? And the state vector is Vm Fk plus the D matrix, which has got to be a 2 by something. The input is a 1 by, or as a 1 vector, so it has to be a 2 by 1 multiplying the input Vs. Okay, so this is going to be our C matrix. And this is, oh, I didn't put our underbars here. This is going to be our D matrix. And Fs, we've got Vm here with a Vm coefficient. So Fs equals negative B Vm plus what Fk? 1 Fk plus what Vs? B. BVS. So that was this equation. And the other equation is Vm equals Vm. So what is the Vm coefficient? 1. What is the Fk coefficient? 0. Vs? 0. And that's it. That is 50% of the next midterm exam probably. Okay? So actually, I would say that this and the final exam, the next 2 midterm exams, a lot of it's going to be coming up with a linear graph model, taking that linear graph model to a state space model. Question?
I'd just like to say this has helped a lot, and I like doing this. And also, I don't understand this as much as I should.
That's okay. We're going to be doing a lot of this. And the lectures, I think there's like 3 examples in the lectures that I do. So this was just an additional one for fun. It's called the mocha problem. I got to come up with a snazzier name for it. The mocha conundrum. Ooh, I like it. Because also that diaphragm thing is a little bit like a drum. Mocha conundrum. Yeah. Word associations in the afternoon. All right. Good job.